This will be a talk on eBPF mostly, and I just wanted to know how many of you are aware of this particular topic, eBPF, and will actually streamline the whole talk accordingly. So, how many of you have heard about this eBPF extended workplace packet or something? And generally, we all are developers, right? We don't have people from college. That's cool. Okay. So, I am actually going to cover a small part of what eBPF is and how this as a developer can help you. So I'll get started with how I went through and how I came across eBPF. So this was through a Grafana meetup here at Chennai. This was, if I'm not wrong, this was 1 year back, where they were actually explaining eBPF along with OpenTelemetry. So eBPF or extended workplace packet filter is something which helps you to get all the data from the kernel. Like right now, you know, kernel programming is actually kind of niche area. We don't go through that. Mostly C developers, C++ developers, or mostly people who actually work in kernel. Other than that, software is all other part which is in the user land. So what is eBPF? eBPF is actually extended workplace packet filter is something which is used to get data out from the kernel. So you remember we had these websites which was totally HTML, like 15, 20 years back. We had website which was totally HTML. There was nothing fancy, nothing popping up, no colors, no CSS, nothing. Then we had JavaScript to actually make things better, make the visualization better, make the UI better, along with having all the functionality which were there in HTML. Same way we have JavaScript for HTML, we have eBPF for kernel level programming. Means it's a hack. It is a hack to get all the data from the kernel without even actually doing kernel level programming. So this is actually a small brief about what eBPF is. And I'll also step into why not kernel programming? Why not the normal kernel programming which everyone does, which every other people do? The first thing is kernel programming is hard. Kernel programming is not for normal developers who is not actually into kernel programming. It has a bit of syntax. It is the whole C++ syntax and everything which core kernel people do might not be easily able to pick it up by software people who do normal web and app. So that is one issue, and the rate of change inside a kernel code is very, very low. Okay, people like people who manage Linux or people who manage all other operating systems, Windows or Mac, they actually are into core level programming and they do kernel level stuff, and the rate of change in kernel code is very low. That is one reason why more developers are not into kernel level programming. And the other point is doing kernel programming is very risky. So if you mess up one line inside kernel programming and you actually deploy it in somewhere, your whole server is actually in risk of going on a breakdown or losing your whole data. So that is why kernel programming is also risky. This eBPF actually gives you a sandbox environment. You are not directly pushing code to the kernel code base. You are not. So my point was kernel programming is a little bit risky for normal developers to do it. eBPF actually gives you a sandbox environment to do your programming, your testing, to get all the data from kernel. This is inside a sandbox environment so that you don't risk writing code into the normal kernel, which might be run in production, so that it doesn't mess up your code. So we are actually going into kernel level programming, and we might need to know 2 to 3 basic things. The first thing is that kernel architecture has two parts. The first part is user space. The second part is the kernel space. So mostly these two words will be used along this presentation. User space and kernel space. It's pretty simple. All the applications we run via UI, what we see, what we touch, what we click, what we type, will mostly be in the user space. And every other thing which helps us get the data, your file directory, your network calls, your file structure, and everything will be inside the kernel lab. So this is a niche area where we might not be directly communicating to, but your user applications will be calling system calls, all the fopen flows and things you do in Python is actually calling this kernel land from the user land. This exchange is costly. So if you're frequently switching from user to kernel, this can add up latency so that your requests can be a bit slow. This is one thing which we might need to take care of. And at last, at the bottom most part, we have the physical layer. Physical layer is hardware, storage network. We'll have a NIC card in most of our devices so that data can come and go through this. So this is the kernel architecture, which we'll be looking forward in the next slide. And how is eBPF doing all things which I explained in the previous slide? I told you that eBPF is actually a way to get inside kernel and do the whole magic. So how is it doing it? We have a user space and we have a kernel space, and we want to do programming or we want to do changes inside the kernel. The eBPF part is a sandbox area like this small b. This area can actually accommodate your program, your code, your script, or anything which will actually wait for a trigger. This trigger can be a network call or a internal file structure call or an fopen or an fclose, anything. So you'll write your program and you'll push this to your kernel, and this eBPF program will sit here idle until an external trigger hits it. So this can be an event. So any event which can trigger this eBPF program will kickstart this application and do whatever you want. We'll actually have a small demo of what I'm talking about and how this eBPF piece is actually helping us. So, yeah. And kernel modifications are also saved with eBPF. And inside the whole eBPF architecture, we have something called as a verifier. So even if we have our code sitting there idle, waiting for a trigger, after this trigger happens, we'll have this code going through a verifier. So this verifier will check that if we have a infinite loop running, or we have some critical section or critical points which can actually damage the whole kernel. So using eBPF is also safe for kernel modification. We will be seeing this infinite loop detected at line 33 in our demo, and which says that the program which we were running was actually having an issue, so that moving forward with this program will actually crash the whole system. Okay, and relying on general kernel programming is also an issue when you have to face all those restarts and all whenever you're doing a kernel change. So if you're doing a kernel level change, you'll have to go through a restart, and this restart can also be costly. We are looking into high level systems. So I'll just give a small demo. So what I have here is two Python programs. The first Python program will be something which actually puts in an eBPF program into the kernel. Every time I use a file which has handsoff.txt, it will actually react. So this is what we are going to do. So I'll just my OS doesn't support eBPF by native, so I'm using an external Ubuntu virtual machine inside my device. So So this is the don't touch.py. I can also show you. Okay. So this will be the Python program which we are going to execute. It has few warnings, which is just to say that we have touched that file. And see, this is the part which I was speaking about. So we have a Python script which actually has a C++ or a C code inbuilt. Okay, so we are actually doing this. We have statically typed C++ function which has a class, a C class, and it is also checking if we touch a particular handler inside kernel. So we will be, yeah. So this is the C function, and every time we touch a file called as handsoff.txt, this will actually give an alert, and the whole code is in C, and this will be the eBPF program which will be embedded into the kernel whenever we run this Python script. We'll go ahead and run this. Okay, so we have this function running right now. I'll also bring up a new terminal. I'll do the same thing there. Okay. So we have a dummy file called as handsoff.txt. So this was the actual file which I wrote in my code, so that every time I touch this code, every time I touch this particular file, I should actually get an alert. Okay, so we'll just try to touch it. We'll just do a cat of handsoff. See, we got eBPF-trace. The Python program is actually telling us that do not look at that file. This is actually a warning which we wrote in our Python script. And if I again try to do the same thing, it will give you the whole warning every time I do it. Okay, cool. Okay, so that was an example where I did take my Python code and put some C++ code, which is then embedded into the kernel level, so that every time I make a system call, it will react according to the logic which is written in Python. So what happened there was, every time I type cat handsoff.txt, the user land is actually giving a system call to the kernel. So this system call is caught by the eBPF program we just deployed into kernel, and every time this call is caught by eBPF, it will actually send a Python script. It will actually send the warning which is written by the Python script. So this is what happened. And I'll also walk through the earlier point I made, which is eBPF programming is kernel safe. So I'll also run the other file, which is fibonacci.py. This is also somewhat similar. We have a C++ code which is running this Fibonacci code piece, and the other part remains the same. Every time I touch a handsoff.txt, it will give out the Fibonacci number. Okay, so I'll try running this. there, we can see that the Python script is running, and I will try to do the same thing here. I'll also get answer.txt, and you can see that the Fibonacci number is coming there. So this is the 40th Fibonacci number which we have mentioned in the code. Okay. So somewhere here we have, yeah, 40th Fibonacci. So we are running this Fibonacci C++ code inside Python, and whenever we are running the Python script, we are deploying this piece of code to the kernel. And every time we get a system call which opens a hands.txt, this kernel is intercepting that code and giving out the returning the Python script and the Python logic. And we'll do one more thing here. We'll just remove the iteration. So what happens if we remove the iteration is that this goes to an infinite loop. So the only thing which is holding this together is the I greater than n and the result being returned. So if I remove that I plus plus, what happens is this goes to an infinite loop. So what happens if an infinite loop goes to the kernels? We'll check that too. Okay. I'll stop this one and I will run the save. Okay. Yeah. So we got the error saying that we have an infinite loop detected at line number 33. So that is why I told you that eBPF programs are also kernel safe. So you can't actually mess up your kernel just by writing eBPF program. This is where I told you that we have a part called as verifier. So we'll see that in the slides, in the remaining slides. But we'll have a verifier which will take all the data coming through eBPF and verifies that if it has any crashback loop or any other infinite loops or code going and messing up your kernel. So we'll go back to the slide. So I'll also walk you through history of eBPF, how eBPF came into existence, from where it began, and what happened. So in 1992, the BPF was born. BPF is Berkeley's packet filter without the whole extended part and everything, which a few people nearly around 2014 built up. So this was designed as a very fast words to get all the kernel data out of the kernel to the user plan. And this at that point allowed some inspection of network packets, doing all the logic on top of that. And then we had few people writing code on top of BPF to get the extended Berkeley packet filter. This was a game changer, which I was talking about. We had a verifier, we had a JIT compiler inside the extended Berkeley packet filter, which was brought on top of the whole BPF. So this even had a virtual machine, which was why whenever I wrote the code which had an infinite loop, it was not disturbing my kernel. It was just stopping it at the level of that sandbox eBPF and beyond. So then, around 2015, we had a thing called as BCC. It is the BPF compiler. And if you notice, we were actually using the same BPF from the BCC library inside Python. So around 2015, we got a compiler which can actually go through the whole eBPF code and do whatever logic and things which you write in Python. And then we had eBPF in networking, and eBPF in networking was actually a game changer. This is the reason why we were able to get packets directly from the NIC, run all the logic on top of that, and we can actually monitor the traffic, we can observe the traffic, analyze, and we can do post analysis over that traffic. So this actually replaced Kubernetes kube proxy. So So pure proxy was actually running on top of IP tables which were hard coded, or we could actually push in some new IP tables. But every time we do this, it was actually taking the O of n algorithmic complexity whenever we do an operation on the IP table. So eBPF had something called as a BPF map, which actually had these details and which could intercept this network calls and give results way faster than what pure proxy does. And now, as I told you, the initial talk I went for the Grafana, they are also discussing things regarding which tightly connects eBPF and OpenTelemetry. So this is currently an ecosystem where OpenTelemetry is very tightly using eBPF for taking all the metrics out of the kernel. We'll quickly go through key features. So as I told you, the one major advantage of eBPF is that it is very efficient in performing all these things. Why? Because this is running in a sandbox environment. It is not disturbing your product. And the same reason that it is sitting inside the kernel will actually allow eBPF to reply faster. It doesn't have to go through kernel user land, and it avoids a lot of context switching. So this saves a lot of time. And then comes safety. As I told you, we won't be messing up the whole kernel code and the whole thing. We will just be playing inside the sandbox environment so that everything is safe. And flexibility. eBPF is actually flexible. It is not inside one particular domain. It can actually range from observability, security, monitoring, and it can also prevent DDoS attacks and all the things inside the security layer. So this is very much flexible. This doesn't depend on any domain. This is basically programming for kernel without even doing any kernel program. So this will also go through how eBPF operates in the kernel. This is something similar which I showed in the demo. So the first thing is to initialize the eBPF program. So this is something similar to installing a camera monitoring system or some sort of that inside an institution or something. So the first thing we do is to initialize the eBPF program or initialize this camera system everywhere inside a building. And then what we do is event triggering. So we'll keep that aside. We'll leave this eBPF program idle until and unless any external trigger comes and hits this eBPF program, this will be active. So the moment an eBPF program is active, it will start collecting all the logs, it will start collecting all the traces and everything, and it will keep it with it unless and until we ask for an analysis. So then we have the execution. So the moment I hit handsoff.txt, the system call was going and we were getting an execution. So it executed the whole Python script, which it was told to do inside the Python program. And that is the execution part. Then we have data collection. So this eBPF program can collect the whole data from kernel at that particular point every time a trigger was hit. And this data can be then used to do post analysis or anything. Sure, we have the analysis part where we can actually take this data, stream it out, and do all the analysis we want. Yeah. So this is how we as developers can actually eBPF. We have a lot of ways here, and the top three ways are for networking, security, and observability. And we have a few things we just use. This is the BCC library which I showed you from where BPF was taken. And Cilium I'll be showing in a demo shortly. And all these SDKs can be integrated with Go, C, Rust, and every other programming language. And the same way I wrote Python code, we could actually write C, Go, or Rust, or anything, and do the whole eBPF magic. And we have a eBPF kernel runtime which actually manages the whole thing. This is the verifier which I was talking about, and the Git compiler, and the bpf map, which has all the networking mappings. So this is how we can use eBPF. Okay. And enhanced observability, I already mentioned that the same way we can actually write a program inside kernel. We can also do observability features on top of that. So the reason being, every time we get a network packet, it is coming to the NIC, to the network interface card. So the very moment we can actually do all those analysis, all those filtering, and all those things at the kernel land. We don't have to wait for this packet to go up till the user land, or so we can actually reduce latency by a big factor. And reduced overhead means that we might not need to do the whole kernel programming and the whole bunch of the things. So we can actually do it inside Python, inside any language which we like, and get the result from kernel. This is the general architecture of eBPF, what it does and how things work. The user program is what we wrote in Python. It had a sequence of code which will be generated as a bpf file code. This will be then sent to the kernel. This is where our eBPF program will be settings. This will initially go to the verifier, which was the place where the Fibonacci failed. The Fibonacci failed because it was creating an infinite loop. And after the verifier passes that, it will go to the BPF. So the program will be sitting there idle until it gets a trigger. So a trigger can be kprop is basically a Python function which inserts all the whole BPF data to the kernel. So whenever it gets a kprop, it is a trigger and it will do whatever things the Python code has done, and it will return the performance output to the user land, which Python told it to do. So this is the eBPF architecture, and yeah, the previous thing I was talking to, it needs a trigger, and this trigger will be hit to a hook. Every time, the last time we did the cat hands off, it was doing an open function system call to the kernel. So this will be going through a hook, eBPF hook. So we'll have my terminal doing a system call which was an open, and this was going to the eBPF program which I wrote on C. And this C will have a whole C program which says that whenever I get this call open for the hands off, just do whatever it is written in C program or in Python. So that is basically a hook. A hook will sit idle until and unless it gets a trigger. We'll also go through some use cases which I was fascinated regarding eBPF. So the first one is network monitoring. I told you that every data packet initially comes to the kernel and initially comes to the network interface card, and then it is tightly coupled with the kernel. So we can actually do a lot more things inside network monitoring. Like one thing is to avoid DDoS or prevent DDoS. So every time a computer is hitting me with 1,000 or 10,000 requests, I can block it in the NIC or in the kernel level itself. I don't have to wait till a WAF or something comes up in the user land. So this is a benefit for network monitoring. And eBPF has something called as an XDP or express data path. This is taking care of the whole data integration and data input and data output. The ingress and ingress go through this XDP. So we can also program that. And performance analysis, as I told you, every application is running on top of kernel. So this data can be streamlined to any system to do post analysis, pre analysis, everything with eBPF. And security and enforcement also similar to DDoS, we can actually have a huge view of the data coming in and coming out, and we can take security measures from that. So we'll also go through a small demo of how many of you have heard of Cilium eBPF? So Cilium is something similar to an eBPF. Cilium is it can act as a L4 load balancer. It can also take in networks and process all the data which we are doing inside the kernel. So the thing I was about to show you was a load balancer which has eBPF functionality, which is taking in data via eBPF, and a normal queue proxy Kubernetes load balancer, which is taking in data without any eBPF or without anything. So we have the results which have a benchmark result of both these load balancers. The only thing to be noted is that the latency values and some requests per second, and we can see that the queue proxy was actually having much bigger latency than compared to the Syrian eBPF. This has a reason why, because we are intercepting this network call at an initial level compared to the queue proxy. And queue proxy is also using an IP table, whereas eBPF was using its own BPF now. And we have that also we have few challenges while doing things inside eBPF. The first thing is it is somewhat difficult to debug into a eBPF program and run through the whole structure. Given that we have an option to write Python, but still we are using some C++ terminology, C++ syntax inside the Python code. Might get complex while debugging, and this will need kernel level concepts to be known by the developer before writing eBPF. So this can also be challenging, and given that we have a verifier, doesn't mean that verifier can actually catch much more complex issues, which can eventually kill the kernel on the server. These are few challenges, and this will be a conclusion slide. So eBPF for enhanced development. It means that eBPF is such a powerful program or powerful framework. Like we as developers, we have that power to make anything, literally anything. We are running on virtual computers, anything virtual. The only thing physical is bits and bytes of data, which is there in the hardware level. So we have this ability to visualize anything and make it happen on a laptop screen. So eBPF is a powerful tool and which can enhance that power of developers to build much more things, to take out much more data from the kernel land and do whatever we need. So yeah, thank you. I can take in questions. If we are doing the observability, in real production systems, people barely care about it. Whether someone is actually in a file. What we usually care about is what is the number of calls that I am getting. That is what I can do is we are doing API gateway monitoring. Take but they expose metrics to the open delivery or something which says like okay, this many requests I got, what is the meaning, how many 200 I got, how many 400 I got, 500 that comes with some bit of overhead for us to maintain anyone who is exposed to that. And I have been reading about eBPF that some of the providers will provide this out of the box solution you can just plug in and then that will expose those. Have you used any such tools or you suggest something like that? Can you suggest something like that? I have not used eBPF specifically to export data. Means the small projects I did, which I showed you, was the maximum which I did to extract few data out of the kernel land. And the same thing which you were talking about, for example, Grafana and OpenTelemetry, everyone in depth is using eBPF to take all the data. So they are actually providers which are internally using it, but not directly using eBPF. So I have not tried anything with that one. And anything which actually triggers a system call to the kernel, we can actually catch it and do any function, any logic in the kernel level. Unless and until we have the system call, we have the freedom to do it. And mostly everything which happens inside a kernel is going through a system call. Yeah, sure. Program base of the program running on the kernel is the base. Yeah, for the program. Yeah, and the kernel is the base for the application. Ordinary and then correct. So what is the overlay name this program on the? So the thing is, the Python script is actually running in my terminal in my user lab. But the C++ code we saw right inside that, it will be injected into the kernel. So the whole traces and the whole system calls coming into the kernel will actually be caught by those hooks. I have placed some hooks inside the C++ code. Every time this hook is intercepted by a trigger, it will act. It will act according to what I have written in the C code. So it is not actually creating any overhead. Suppose we have 10,000 lines of kernel code. I am just adding like 50 lines more. So you are editing the kernel. I am actually pushing some code to the sandbox environment of eBPF, which is sitting inside the same kernel. It's inside that sandbox. If there is any query comes, then the trigger happens to the kernel level. Correct. So that's what you mentioned. It is acting within the request form. Otherwise, yeah, it's idle. Every time we have a trigger, it will actually act. Yeah. Okay. Yeah. So what are we actually monitoring? When there is edit in the file, what kind of edit in the file or kind of a monitoring, right? Something happens. What are we trying to capture? Is it an attack happen at the application server or is what are we trying? You're talking about the example which I gave, right? The demo. Okay. So that was actually a dummy thing, but what we can extend is from that particular project itself, it was taken from a project which is looking for the most used file inside an operating system. Okay, the same program was taken from that a big chunk of code. Most used file inside an operating system. So every time you are hitting S open or a S close, F open or an F close, you are actually sending a kernel message or a system call. So we are tracing that particular system call and checking which file is opened most number of times. This can also be linked to security. So if we can detect anomalies in opening or closing a file, this can be reported and this can be pushed to a team or something. So this can be customized to any level. Yeah, definitely. Any level of files in the operating system and application. We have the liberty to actually write logic on top of that so that whatever we need inside kernel, we can get it. We can do analysis on top of that and just rest the eBPF program there until the trigger comes. After this level also we have the audit. The auditing of also can be taken. Yeah. It is if we wish to create a software which uses eBPF to get all the metrics out, we can actually represent it. This is up to the developers to explore. Yeah. On similar line over. How do you monitor this? Way to monitor what? So you are taking something that can code how do you ensure that? I have not been through that deep. The only thing is kernel is the base, right? We don't have something beneath that. So we are writing crack code inside kernel, it will obviously ruin the whole server and the whole. So general principles, I'm not sure. I have not went through that. I am actually exploring the whole eBPF and building the project. Yeah. You can't actually do it inside kernel. You'll have to give it back to the user land and store it in a DB array. Why? Because kernel storage is specifically for kernel. We can't just put junk and dump the work. Push it to user land and store it. And that's okay. No. That means you will have one context switch from user to kernel to user. There's just two context switching. The issue is when you do frequent context switching, like 10, 20, or those. This is sorry. Within a single project. This is generally happening whenever we are clicking a button and everything. We are going up and pro kernel and user. Yeah. This is something similar to an event listening.
So does it run a back set the file open request and then hands it back to another.
This actually is residing somewhere inside kernel. Every time a system call comes to the kernel, this will catch it and check if this is something to do with the program which we have written in C. And if it has something to do with the program, and if the system call is coming somewhere in the program we have, why? Because we have written that this function call which opens a file, we should be going and checking if that file name has answer.txt. Okay, so that will be residing there. Even if whenever we have a trigger, it will be opening up and it will pushing all the warnings. It intercepts the system call.
So will I be able to
what arguments?
Was the request was to open a file.
Correct.
And I intercept change the file name.
You want to change the file name from the kernel.
Request to open a file in directory 1. Instead, open directory 2 and use the file name.
You're actually trying to move a file or change the file name.
The program wants to open 1. I have to open 2.
So fopen is one such system call which I was using, and renaming will have a different system call.
It's trying to open 1. The program should think that it is opening 1, but instead it should be actually done. Suppose I'm giving letter request from 1.
Okay, user land is actually say opening a file.
Yeah, user land is opening
file 1. So system call is going to kernel, saying that file 1 is getting opened.
Yeah, but before, instead of getting the file 1 handler, file 2 handler. According to the user land, it's actually file 1, but underneath the storage, what happens is file.
This is actually one way, right? User land is actually saying that file 1 is open, and kernel is actually responding. You can't actually say that file 2 is coming. Kernel doesn't have that thing. Kernel is actually responding to what user land is giving, and then acting on top of it.
Yeah, so it's
it will listen to the whole system call coming to kernel, and it will act on top of it. It is basically listening everything.
It is listening, not changing the.
Not changing anything inside the file. Anything inside the file. We can actually do it. Why? Because if we have a system call to edit a file, we can actually do that. Okay, but here in my program, what it is doing is it is just looking for an fopen or any changes to that particular file, and it is acting on top.
We can't change the file name.
No, not from the kernel. If user land is actually initiating it, we can do it.
There's also a change because there's a way to build out requests.
Yeah, we can.
In that case, you're actually shutting down the kernel.
The thing is, how DDoS can actually work in user land is that a request will come to the network interface card, which is inside the kernel. Not inside the kernel, it's the hardware, but tightly linked to the kernel. This request can come, and this thing should go to the user land and check if everything is fine. If we have these many requests per second, if that is okay, we'll just allow it. If it is not allowed, we'll simply block it and then send kernel a request back saying that this is not something what we expect. Just block it. What eBPF does is that as soon as you get these 1,000 requests per second, eBPF has this logic, the same logic which I was explaining. So this will act as a trigger. 1,000 requests coming per second will act as a trigger, and it will run the eBPF program and stop that particular network as it is. So it won't just jump to user land and expect it to come back. So we have this. Cool. Thank you.